Close your eyes and let your thoughts float beyond the confines of the everyday. Let your imagination reach toward the infinite expanse above, where countless stars twinkle in serene stillness. The universe is not merely vast, it is boundless, mysterious, and endlessly captivating. It stretches beyond comprehension, beckoning us to explore its secrets and marvel at its wonders. Have you ever wondered what lies beyond the twinkling lights in the night sky, or what forces are at play in the dark, silent stretches of space? Tonight, as you ease into the rhythm of your breath and the calming hum of this journey, we will wander together through some of the most fascinating, profoundly lost truths of the universe. This isn't a tale of urgency or final answers, but a peaceful exploration of cosmic riddles, perfect to lull your mind into curiosity and calm. The universe is not just a realm of science and numbers, it's a storyteller spinning tales of creation, destruction, and evolution over billions of years. It is a place where science meets imagination, where questions multiply the more we learn. While our understanding grows, so does the realization that much remains beyond our grasp. The allure of the unknown isn't about the answers, it's about the questions. What lies in the silent voids between galaxies? What unseen forces weave the threads of time and space? What mysteries are locked in the light of stars that died eons ago? Their stories now reaching our eyes. As vast as the universe is, its secrets are even greater, inviting us to wonder, imagine, and dream. Tonight, we let these mysteries guide us, not to solve them, but to appreciate their beauty. From the shadowy presence of dark matter to the invisible force of dark energy that drives the universe apart, the cosmos is filled with phenomena that defy understanding. What is the great attractor, and why does it pull entire galaxies toward it? Could there be other universes beyond our own, as the multiverse hypothesis suggests? And what of the Fermi paradox, the haunting silence from the stars, asking why, if the universe is so vast, we seem so alone? These mysteries, and others, form the fabric of our journey. We will glide through ancient star systems, ponder the fate of the universe itself, and delve into anomalies like Oumuamua, a fleeting visitor from another star system whose origins remain unknown. Each mystery is a thread in the intricate tapestry of the cosmos, woven into patterns we can only begin to discern. As you listen, let these cosmic enigmas quiet the day's chatter and replace it with the gentle hum of wonder. There is no rush, no urgency, only the endless flow of time and the peaceful rhythm of discovery. Each mystery reminds us of how small yet significant we are, suspended in a universe too vast to comprehend. The beauty of the unknown lies not in answers, but in possibilities. The mysteries of the cosmos are not obstacles to understanding, they are invitations to dream. And so, we begin our journey. The first mystery awaits us, a doorway to the infinite, where science and imagination intertwine. Together, we'll drift through the cosmic expanse, exploring phenomena that challenge our understanding and spark our curiosity. Let the universe guide your thoughts as we embark on this tranquil voyage. Mystery 1, the void. Celestial emptiness amid cosmic abundance, the vast nothingness. Imagine a region so vast that it stretches hundreds of millions of light years, yet contains almost no galaxies, stars, or visible matter. This is the Bootes void, one of the largest known voids in the universe, spanning an area so empty it has often been referred to as a supervoid. Its discovery in 1981 by astronomers Stephen Gregory and Laird Thompson stunned the scientific community, raising profound questions about the structure and evolution of the cosmos. While the universe is predominantly space, the Bootes void is an extreme case of isolation. In contrast to the densely packed regions of galaxy clusters, this cosmic expanse contains roughly 60 galaxies, a stark deviation from what scientists expect based on the universe's distribution of matter. Formation theories, a cosmic puzzle. How could such emptiness arise in a universe governed by gravitational forces pulling matter together? One theory suggests that the void formed as smaller, individual voids merged over time, like bubbles coalescing in a frothy liquid. This model aligns with simulations of large-scale cosmic structures where interconnected voids and filaments shape the universe into a vast cosmic web. Another hypothesis delves into the quantum nature of the universe's birth. Fluctuations in the primordial soup of particles during the Big Bang might have led to uneven distributions of matter. The Buati's void, then, could be a relic of those early imbalances, preserved through billions of years of cosmic evolution. The role of dark matter and energy. The void also provides a unique testing ground for dark matter and dark energy, the enigmatic forces that dominate the universe. Some scientists suggest that interactions between visible and dark matter might suppress galaxy formation within voids. Dark energy, which drives the universe's accelerated expansion, could amplify such regions over time, pushing matter outward and deepening the void's emptiness, a window into cosmic isolation. Despite its emptiness, the Buotis void is not entirely devoid of intrigue. The sparse galaxies within it offer a unique opportunity to study cosmic evolution in isolation. These galaxies may have followed a developmental path distinct from those in dense clusters, potentially harboring clues about star formation, galactic interactions, and the effects of isolation on cosmic objects. One of the most captivating ideas surrounding voids like Buotes is their potential as windows into the underlying structure of space-time itself. Their vast emptiness reduces interference from surrounding matter, making them ideal for studying gravitational waves, cosmic microwave background radiation, and even the effects of dark energy on space-time curvature. Beyond its scientific implications, the Buotes void invites profound philosophical contemplation. In a universe so vast and varied, why does such emptiness exist? It challenges human perceptions of balance and order, reminding us that the cosmos operates on principles often beyond our intuitive understanding. The void's sheer scale and isolation evoke a sense of awe, underscoring the fragility and rarity of matter within an overwhelmingly empty universe. Future exploration. As observational technology improves, astronomers hope to uncover more about voids like Buotes. High-resolution surveys and simulations may reveal the mechanisms behind their formation and growth, while advanced telescopes could peer deeper into their recesses to study faint, hidden galaxies. Understanding these vast voids might not only answer questions about their origins, but also provide insights into the universe's ultimate fate. Concluding thoughts on the void. The Buotes void stands as a testament to the universe's ability to surprise and confound. In its emptiness lies the story of cosmic evolution, the interplay of forces shaping the cosmos, and humanity's enduring quests to understand the unknown. As we peer into this vast chasm, we are reminded that even in the absence of light and matter, the universe speaks volumes. Mystery 2, Oumuamua, the Interstellar Enigma, the arrival of a visitor from afar. In October 2017, astronomers using the Pan-STARRS 1 telescope in Hawaii detected an object unlike anything ever observed before. Named Oumuamua, meaning scout or messenger in Hawaiian, it was the first known interstellar object to visit our solar system. Measuring approximately 800 meters in length and shaped like a flattened cigar, Oumuamua's trajectory and velocity confirmed its origin beyond our solar system, sparking intense curiosity and debate about its nature. A peculiar path. Unlike any comet or asteroid previously observed, Oumuamua exhibited several anomalies that defied easy classification. Its hyperbolic trajectory, unbound by the sun's gravitational pull, indicated it was merely passing through, never to return. The object's tumbling motion, combined with an unusual brightness that fluctuated dramatically, suggested a unique, elongated shape or possibly an uneven surface. More puzzlingly, Oumuamua exhibited a slight but noticeable acceleration as it exited the solar system. This behavior, typically associated with comets, was perplexing because Oumuamua lacked the visible Quasar cloud of gas and dust commonly seen when a comet is heated by the sun. This absence raised questions about what might be propelling it. Theories of origin and nature. Scientists proposed a range of hypotheses to explain Oumuamua's peculiarities. One theory posits that Oumuamua might be a fragment from a larger planetary body or asteroid that was ejected from its home system following a cataclysmic event. Its elongated shape and metallic or rocky composition could point to this violent origin, a comet without a coma. Some researchers suggest that Oumuamua might be an icy body coated with a carbon-rich crust, preventing the release of visible gas and dust. Its slight acceleration could be caused by the sublimation of volatile ice beneath the surface. The ice remains undetectable with current instruments. An alien artifact? Perhaps the most controversial hypothesis is that Oumuamua could be an artificial object, such as a defunct probe or a piece of extraterrestrial technology. Harvard astronomer Avi Loeb popularized this idea, proposing that its peculiar shape and unexplained acceleration might indicate it is a light sailor, a thin, reflective material propelled by solar radiation or another propulsion mechanism. Implications for interstellar exploration. Oumuamua's brief visit provides a tantalizing glimpse into the vast expanse of interstellar space. If it is a natural object, it offers clues about the processes shaping distant star systems and their planetary debris. Its trajectory suggests that interstellar objects might be more common than previously thought, raising the possibility that other visitors from beyond our solar system await discovery. From an astrobiological perspective, interstellar objects, like Oumuamua, might serve as carriers of organic material or even microbial life, potentially seeding planets as they traverse the cosmos. This panspermia hypothesis underscores the interconnectedness of the universe and the potential for life to spread across vast distances. Technological and observational challenges. The fleeting nature of Oumuamua's visit highlights the limitations of current observational technologies. By the time it was detected, the object was already receding from the Sun, moving too fast for detailed study. Future detection systems, such as the Vera C. Rubin Observatory, are expected to improve our ability to identify and study such objects earlier in their approach, enabling more in-depth exploration. Philosophical reflections on Oumuamua. Oumuamua's mysterious nature has also inspired philosophical contemplation. Its journey through the solar system serves as a reminder of the interconnectedness of the universe and humanity's role as observers of its wonders. The possibility, however remote, that it could be an artifact of intelligent design challenges our understanding of our place in the cosmos and rekindles the age-old question, are we alone? Future prospects and missions. While Oumuamua itself is now beyond reach, its discovery has galvanized interest in studying interstellar objects. Proposed missions, such as Project Lyra, aim to intercept future visitors or even catch up to objects like Oumuamua. These missions would provide an unprecedented opportunity to analyze the composition, structure, and origin of interstellar travelers, potentially unlocking new secrets of the cosmos. Oumuamua's brief sojourn through our solar system may have raised more questions than it answered, but its significance cannot be overstated. As the first interstellar object ever observed, it has expanded our understanding of the universe's vastness and complexity. Whether a natural fragment, a cometary anomaly, or something entirely unexpected, Oumuamua remains a symbol of the mysteries that lie beyond the stars, a messenger from the unknown urging humanity to look outward and wonder. Mystery 3. Quasars and their intense energy, beacons of the early universe. Quasars, or quasi-stellar objects, are some of the most energetic and luminous entities in the universe. First discovered in the 1960s, these celestial phenomena are characterized by their incredibly bright emissions, outshining entire galaxies, despite being no larger than our solar system. Quasars are thought to be powered by supermassive black holes at the centers of distant galaxies, surrounded by swirling disks of gas and dust. As material falls into these black holes, it is accelerated to near light speeds, generating intense radiation across the electromagnetic spectrum. Quasars often appear as brilliant points of light, their energy output so immense that they can be observed billions of light years away. acting as cosmic lighthouses from the early universe, a window into the past. Quasars are not merely objects of intrigue for their brightness, they are also windows into the distant past. The light from quasars takes billions of years to reach Earth, allowing astronomers to study the conditions of the early universe. The farthest quasars we observe today were active when the universe was less than 1 billion years old, providing critical insights into the formation of galaxies and the role of black holes in shaping cosmic structures, the puzzle of their power. The energy output of quasars is staggering. Some can emit the energy equivalent of 1 trillion suns. This immense luminosity raises questions about their feeding mechanisms. How do supermassive black holes accrete enough material to sustain such high levels of energy production? Accretion disks. The leading explanation lies in the accretion disk, a structure of gas and dust spiraling into the black hole. As material accelerates and heats up, it emits vast amounts of radiation, making quasars visible across vast cosmic distances, jets and magnetic fields. Some quasars also emit powerful jets of plasma, extending for thousands of light years. These jets, thought to be shaped by the black hole's intense magnetic fields, channel energy into the surrounding intergalactic medium, influencing galaxy formation and evolution. Anomalies in quasar observations. Despite decades of study, quasars continue to confound astronomers with their peculiar behaviors and unexpected properties. Changing look quasars. Some quasars have been observed to change their brightness levels dramatically over relatively short periods, years or even months. This phenomenon, known as changing look quasars, challenges existing models of black hole accretion and suggests dynamic processes at play. Superluminal motion. Jets emitted by quasars often exhibit apparent superluminal motion, appearing to move faster than the speed of light. This optical illusion, caused by relativistic effects, underscores the extreme environments and velocities near quasars. Quasar clustering. Recent studies have revealed unexpected clustering of quasars, suggesting large-scale structures in the early universe that defy conventional models of cosmic evolution. The role of quasars in cosmic evolution. Quasars are more than just luminous beacons. They play a pivotal role in the evolution of galaxies and the universe as a whole. The energy released by quasars can influence their host galaxies in several ways. And now we're coming to the part where we entertain a new invitation. Feedback mechanisms. The radiation and jets emitted by quasars can heat surrounding gas, suppressing star formation in the host galaxy. This feedback mechanism is believed to regulate galaxy growth and explain the observed relationship between galaxies and their central black holes. Chemical enrichment. Quasars contribute to the chemical enrichment of the intergalactic medium, dispersing heavy elements forged in stars across vast distances through their powerful outflows. Quasars as tools for exploration. Quasars are invaluable tools for studying the universe's large-scale structure. By analyzing the light from quasars, astronomers can map the distribution of matter across billions of light years. For example, the light from distant quasars passes through intergalactic clouds of hydrogen, creating absorption lines known as the Lyman-Alcott forest. These lines provide a detailed map of the universe's large-scale structure and its evolution over time. Quasars serve as cosmic markers, helping scientists measure the rate of the universe's expansion and investigate the mysterious nature of dark energy. Quasars and the search for extraterrestrial life. While quasars are not directly linked to the search for extraterrestrial life, their extreme environments and energetic processes raise intriguing possibilities. Could advanced civilizations harness the immense energy of quasars, as some speculative scenarios suggest? Or might quasar activity influence the habitability of galaxies, shaping the conditions for life to emerge? Future observations and theoretical challenges. Despite significant advances, many questions about quasars remain unanswered. Upcoming telescopes, such as the James Webb Space Telescope and next-generation radio arrays, promise to shed new light on these enigmatic objects. Key questions include: what triggers quasar activity? in certain galaxies. How do quasars evolve over cosmic time? What can quasars reveal about the interplay between black holes and their host galaxies? Quasars represent the extremes of the cosmos, both in terms of energy and distance. They challenge our understanding of physics, cosmic history, and the nature of black holes. As we peer deeper into the universe and uncover new details about quasars, we not only unravel the mysteries of these extraordinary objects, but also gain a richer understanding of the universe itself. Mystery 4. The Great Attractor, the unseen cosmic force. Deep in the heart of the universe lies a region known as the Great Attractor, a mysterious gravitational anomaly that has perplexed scientists for decades. This unseen force, located roughly 150 million light-years away in the direction of the Centaurus and Hydra constellations, is pulling vast numbers of galaxies, including our own, toward it with immense force. But despite its significant influence, the Great Attractor remains largely invisible to observation, making it one of the most perplexing phenomena in modern astronomy. What is the Great Attractor? The Great Attractor is not a single object, but rather a region of space that contains an enormous concentration of mass. The gravitational pull exerted by this mass causes galaxies in our local universe to move toward it at high velocities. Unseen gravity. The Great Attractor is invisible because it resides behind the zone of avoidance, a region of the sky heavily obscured by the plane of our Milky Way galaxy. Dust, gas, and stars in our galaxy make it difficult to see the exact source of the gravitational pull, but it is believed to be a massive, dense concentration of galaxies and dark matter. The motion of galaxies. The pull of the Great Attractor is so strong that it is causing the entire local group of galaxies, including our own Milky Way, to accelerate toward it at a velocity of over 600 kilometers per second. This motion is part of the larger cosmic flow that drives the motion of galaxies on a grand scale. But the Great Attractor is by far the most significant influence in our immediate cosmic neighborhood, the hunt for the source. Since its discovery in the 1970s, the Great Attractor has been a subject of intense study and speculation. However, scientists still struggle to fully understand the nature of this anomaly and the exact source of the force pulling galaxies toward it. The Shapley Supercluster. One candidate for the source of the Great Attractor's gravitational pull is the Shapley Supercluster, a massive concentration of galaxies located at the center of the Great Attractor. This supercluster is one of the largest structures in the observable universe, with a mass more than 1,000 times that of the Milky Way. However, recent observations suggest that the Shapley Supercluster alone cannot account for the full force observed. This raises the possibility that the Great Attractor's influence may also involve large quantities of dark matter or other unknown cosmic structures. Dark matter and theories of large-scale structure. Theories suggest that the Great Attractor could be the center of a vast mass of dark matter, a substance that makes up a significant portion of the universe's total mass, but does not emit light, making it nearly invisible. Dark matter is thought to influence the motion of galaxies, and its concentration in the Great Attractor could explain the strong gravitational pull observed. The role of dark matter. Dark matter, which has eluded direct detection for decades, plays a central role in many theories about the Great Attractor. The mysterious motion of galaxies in the region may be one of the clearest signs of dark matter's existence. While dark matter cannot be observed directly, its presence is inferred by its gravitational effects on visible matter, a dense gravitational sink. One of the leading hypotheses is that the Great Attractor is a large gravitational sink, composed mostly of dark matter. This would mean that the dark matter in the region is not only contributing to the gravitational pull, but also influencing the movement of galaxies over vast distances. Implications for cosmology. The Great Attractor's gravitational effects also have broader implications for our understanding of the large-scale structure of the universe. If dark matter plays such a pivotal role in cosmic motion, it could help explain the distribution of galaxies and galaxy clusters across the universe, offering new insights into the formation and evolution of large-scale cosmic structures. Anomalies and unanswered questions. Despite numerous observations and theoretical models, the Great Attractor still presents several anomalies and unanswered questions. Plainly, everything about life still remains unclear. Anomalous velocity flows. The movement of galaxies toward the Great Attractor is not entirely smooth. There are significant discrepancies in the expected velocities, with some galaxies exhibiting speeds that are higher than predicted by models. These anomalies suggest that other forces or factors may be at play in the region. The void conundrum. In contrast to the dense mass of the Great Attractor, there exists a void in the region surrounding it, a massive, nearly empty region of space. This void, often referred to as the dipole repeller, is thought to be pushing galaxies away from the Great Attractor. The interaction between the Great Attractor and the void is another layer of mystery that scientists are only beginning to unravel. Cosmic flow and large-scale structure. The existence of the Great Attractor challenges our understanding of how galaxies and galaxy clusters move through space. The concept of cosmic flow, or the general movement of galaxies, has become a central part of research into large-scale structures. The Great Attractor's pull is one of the strongest known sources of such flow. However, its precise location, composition, and role in shaping the structure of the universe remain unresolved. While the discovery of the Great Attractor has provided important insights into the universe's large-scale structure, many questions remain unanswered. Theories about its nature, composition, and the exact cause of the forces at work continue to evolve as new data is gathered from both ground-based and space telescopes. Ultimately, the Great Attractor is a reminder that the universe is filled with enigmatic forces, many of which remain hidden from our direct view. As we continue to probe the depths of space and time, the mysteries of the Great Attractor offer a tantalizing glimpse into the hidden mechanics of the cosmos. Mystery 5. Dark matter and dark energy, the invisible forces of the universe. The concepts of dark matter and dark energy represent two of the most intriguing and mysterious aspects of the cosmos. Together, they make up around 95% of the total mass and energy content of the universe. Yet they remain largely invisible and undetectable through direct observation. Despite their profound influence on the structure and evolution of the universe, we still have very little understanding of their true nature. Dark matter, the hidden mass. Dark matter, which constitutes about 27% of the universe's total mass energy's content, is a hypothetical form of matter that does not emit, absorb, or reflect light, making it invisible to traditional telescopic observations. It was first proposed by Swiss astronomer Fritz Zwicky in the 1930s, who observed that the galaxies within galaxy clusters were moving much faster than could be explained by the visible matter they contained. Zwicky hypothesized that there must be some unseen mass in these clusters to account for the gravitational forces that were holding them together. Since then, multiple lines of evidence have reinforced the existence of dark matter, even though it remains undetected by all direct means. One of the most compelling pieces of evidence for dark matter comes from the study of galactic rotation curves. When scientists observe the motion of stars in galaxies, they find that the stars on the outer edges of galaxies are moving much faster than would be expected based on the amount of visible matter in the galaxy. According to Newtonian physics, these stars should be moving slower. But the Dofaus, they do not suggest the presence of unseen mass exerting a gravitational pull. Another key piece of evidence comes from gravitational lensing, a phenomenon in which massive objects, such as galaxy clusters, bend light from more distant sources. The amount of bending observed in these cases is far greater than expected from visible matter alone, again suggesting the presence of additional unseen mass. Despite extensive searches, dark matter has not been directly detected. Scientists have proposed several potential candidates for what dark matter might be, including weakly interacting massive particles, WIMPs, axions, and sterile neutrinos. However, none of these hypothetical particles have been observed, and the exact nature of dark matter remains one of the biggest mysteries in physics. Dark energy, the accelerating force. While dark matter is thought to exert a gravitational pull, dark energy, which makes up approximately 68% of the universe, is believed to be responsible for the accelerated expansion of the universe. Dark energy was first inferred in the late 1990s when astronomers discovered that the rate at which the universe is expanding is increasing, rather than slowing down, as had been expected. This observation was based on the study of distant supernovae, which appeared dimmer than expected, indicating that they were farther away than previously thought. The only explanation for this observation was the existence of some form of energy that is pushing galaxies apart, counteracting the force of gravity and causing the expansion of space itself to accelerate. Since then, dark energy has become a central focus of cosmological research. Although its exact nature remains a mystery, dark energy is thought to have a negative pressure that causes the universe to expand at an ever-increasing rate. Some theories suggest that dark energy is a property of space itself, while others propose that it could be related to quantum fluctuations in the vacuum of space. However, the true nature of dark energy is still unknown, and it remains one of the most enigmatic and controversial topics in cosmology. Evidence for dark matter and dark energy. Despite the challenges in detecting dark matter and dark energy directly, there is a wealth of indirect evidence supporting their existence. From the cosmic scale down to the behavior of individual galaxies, the effects of these invisible forces are apparent in numerous aspects of the universe. Galaxy clusters. As mentioned earlier, one of the primary sources of evidence for dark matter comes from observations of galaxy clusters. The gravitational lensing observed in these clusters provides a map of the present but unseen dark matter. The amount of dark matter inferred from gravitational lensing observations is consistent with the observed motion of galaxies within clusters, further supporting the theory that dark matter exists and plays a significant role in the structure of the universe. Cosmic microwave background, CMB. The cosmic microwave background, the faint glow left over from the Big Bang, provides crucial evidence for both dark matter and dark energy. By studying the temperature fluctuations in the CMB, scientists can infer the density and distribution of both visible and invisible matter in the universe. The patterns observed in the CMB provide a snapshot of the universe when it was just 3,800,000 years old, and these patterns have been used to estimate the amount of dark matter and dark energy in the universe. Large-scale structure of the universe. Another source of evidence for dark matter comes from the distribution of galaxies in the universe. The large-scale structure of the universe is how galaxies and galaxy clusters are arranged. Can only be explained if a significant portion of the universe's mass is invisible. Dark matter is thought to provide the gravitational framework that shapes this structure, with galaxies and clusters forming along the filaments of dark matter. The mystery of their nature. Despite the overwhelming evidence for the existence of dark matter and dark energy, their true nature remains elusive. Numerous experiments have been conducted in an attempt to detect dark matter particles directly, but none have been successful so far. One of the primary challenges is that dark matter does not interact with electromagnetic radiation, meaning it cannot be seen through telescopes or detected with traditional instruments. This has led scientists to explore a variety of theoretical models, but so far, no conclusive evidence has emerged to pinpoint the exact nature of dark matter. Similarly, the mystery of dark energy is just as profound. While its effects are observed on cosmological scales, scientists are still unsure what dark energy is. Some theories suggest that dark energy is a cosmological constant, a form of energy inherent to space itself, while others propose that it could be related to the quantum vacuum. Recent advances in observational techniques and data collection may one day provide the breakthrough needed to unravel the true nature of dark energy. But for now, it remains a cosmic riddle. Implications for the universe. The implications of dark matter and dark energy are profound and far-reaching. If dark matter is indeed the unseen mass responsible for the formation of galaxies and galaxy clusters, then it fundamentally alters our understanding of the universe's structure. Without dark matter, the universe would look vastly different, with galaxies unable to form and gravitational forces acting differently on all scales. Similarly, the role of dark energy in accelerating the expansion of the universe has dramatic consequences for the ultimate fate of the cosmos. The fate of the universe. The influence of dark energy suggests that the universe will continue to expand forever, driven by the accelerating force of this mysterious energy. This has led to various theories about the long-term future of the universe, including the possibility of a big freeze, where galaxies move farther and farther apart until all stars burn out and the universe becomes cold and dark. The continued expansion could eventually lead to a big rip, where the fabric of space-time itself is torn apart. However, these outcomes depend heavily on the properties of dark energy, which are still not fully understood. A continuing enigma. Dark matter and dark energy represent some of the greatest mysteries of modern science. Together, they make up nearly 95% of the universe, yet we have little understanding of what they are or how they function. As research continues and new technologies are developed, scientists remain hopeful that these elusive forces will eventually be understood, revealing some of the deepest secrets of the cosmos. Until then, dark matter and dark energy will remain as invisible, yet essential, components of the universe, shaping its past, present, and future in ways we are only beginning to comprehend. Mystery 6. The Multiverse Hypothesis. The multiverse. Beyond our universe, the idea of a multiverse, the existence of multiple, perhaps infinite universes, is one of the most mind-boggling and profound concepts to emerge from the frontiers of modern physics. The multiverse hypothesis suggests that the universe we inhabit is just one of many distinct universes, each with its own set of physical laws and constants. While this may sound like science fiction, it arises from serious scientific theories and has been the subject of intense debate and research. The origins of the multiverse idea. The multiverse hypothesis finds its roots in various branches of theoretical physics, particularly in the realms of cosmology, quantum mechanics, and string theory. It presents a radical shift in our understanding of reality, challenging the notion that our universe is the only one in existence. The multiverse theory proposes that there may be an endless number of universes, each potentially vastly different from the others. Cosmic inflation and the birth of universes. One of the most compelling arguments for the multiverse comes from the theory of cosmic inflation, which posits that the universe underwent an incredibly rapid expansion in the first few moments after the Big Bang. According to this theory, inflationary processes could lead to the formation of pocket universes, each emerging from its inflationary bubble. These universes could vary in size, structure, and fundamental properties, and might even have different physical laws than our own. This gives rise to the idea that our universe could just be one of an infinite number of such bubbles. String theory and extra dimension. String theory, which attempts to unify the forces of nature into a single framework, also predicts the existence of extra dimensions beyond the familiar 3 dimensions of space and one of time. In some versions of string theory, the interactions of these extra dimensions could give rise to an entire landscape of possible universes, each with its unique characteristics. These universes might have different constants, particle properties, or even entirely different forms of matter and energy. Types of multiverses. Not all multiverses are the same, and the hypothesis encompasses a variety of different models, each with its implications. These models differ in how they describe the nature of these universes and how they relate to one another. Understanding the different types of multiverses provides a deeper insight into the potential scope of the concept. The Level 1 Multiverse. The Level 1 Multiverse refers to the idea that space itself is infinite, meaning that beyond the observable universe there are regions of space that are too far away to ever be observed. In this infinite space, there would be regions where conditions are nearly identical to our own, leading to the possibility of identical or almost identical copies of our universe. These regions could be considered parallel universes, and they are separated by vast distances, making them effectively unreachable. The Level 2 Multiverse. The Level 2 Multiverse emerges from the theory of cosmic inflation. According to this model, the universe we live in is just one of many bubble universes that are constantly forming in a much larger multiverse. Each of these bubbles could have different physical constants, such as varying strengths of gravity, or electromagnetism, which could lead to vastly different forms of matter and energy. The key feature of the Level 2 multiverse is the idea that each bubble universe can have different laws of physics, allowing for the existence of entirely foreign types of universes. The Level 3 multiverse. The Level 3 multiverse arises from the interpretation of quantum mechanics known as the many worlds hypothesis. In this version of the multiverse, every quantum event that can have multiple outcomes leads to the creation of a branching universe. For example, when you make a decision, every possible outcome happens, but in a different branch of the universe. This creates a vast and ever-growing number of parallel realities, with each quantum interaction spawning a new universe. This model suggests that every action, decision, and event has the potential to create a separate, alternate universe, leading to an incredibly complex multiverse. The Level 4 multiverse. The Level 4 multiverse is perhaps the most radical and abstract of all. In this concept, proposed by physicist Max Tegmark, the multiverse is defined as a collection of all mathematically possible structures, including those that may not conform to any recognizable laws of physics. This multiverse encompasses not only universes with different physical constants and properties, but also universes that are based on entirely different mathematical frameworks. In this model, the multiverse includes every conceivable form of reality, whether or not it conforms to the laws of physics that we recognize. Evidence and controversy. While the idea of the multiverse is intriguing, it has also been met with skepticism, as it presents challenges to empirical validation. Since the other universes, by definition, lie beyond our observational capabilities, it is difficult, if not impossible, to gather direct evidence for their existence. This has led some scientists to argue that the multiverse hypothesis falls outside the realm of testable science, and should therefore be considered more of a philosophical or speculative concept than a scientific theory. Indirect evidence. Despite the lack of direct observational evidence, some indirect pieces of evidence suggest the possibility of a multiverse. For example, the fine-tuning problem in cosmology, which asks why the fundamental constants of nature appear to be so perfectly suited for life, could be addressed by the idea of a multiverse. In a multiverse, there would be many universes with varying constants, and we happen to live in one that is conducive to life. This kind of reasoning leads some to argue that the multiverse hypothesis could provide an elegant explanation for the apparent fine-tuning of the universe. Theoretical models and predictions. Another avenue of evidence comes from the mathematical models used to describe cosmic inflation and string theory. These models predict that a multiverse is not only possible, but likely. While these predictions cannot yet be tested directly, they provide a foundation for further theoretical exploration. Philosophical implications. The multiverse hypothesis also raises deep philosophical questions about the nature of reality and our place in the cosmos. If there are an infinite number of universes, each with its own set of physical laws, what does that mean for the uniqueness of our universe? Are we just one among countless others, or is our universe special in some way? The multiverse concept also challenges our understanding of determinism, free will, and the very nature of existence. The Anthropic Principle. One philosophical consideration tied to the multiverse is the Anthropic Principle, which posits that the universe must be compatible with the existence of observers, such as us, who can contemplate its existence. In a multiverse, the Anthropic Principle suggests that we find ourselves in a universe that is fine-tuned for life, because, in an infinite multiverse, there must be some universes where conditions are favorable for life. The principle has sparked debates about the nature of reality and our place within it, leading to a broader philosophical exploration of existence itself, a cosmic puzzle. The multiverse hypothesis is a concept that straddles the line between cutting-edge science and speculative philosophy. It challenges our understanding of the universe and raises profound questions about the nature of reality. Whether or not the multiverse is a scientific fact or a fascinating theory remains to be seen, but it certainly opens the door to a vast and unexplored realm of possibilities. If the multiverse exists, it will change our entire perspective on the universe and our place within it, offering a cosmic puzzle that may never be fully solved, but will continue to captivate the imagination for generations to come. Mystery 7. Time and temporal anomalies. The elusive nature of time. Time, the very fabric of our reality, is one of the most familiar yet most mysterious aspects of the universe. It is the medium through which all events unfold, yet its true nature remains elusive. Time flows forward, unidirectional, or so it seems. But scientists have uncovered a series of anomalies that challenge our basic understanding of temporal mechanics. From theoretical physics to quantum mechanics, time anomalies present a fascinating paradox. While we typically think of time as a simple, linear progression, certain phenomena in the cosmos indicate that time might not be as straightforward as we assume. Temporal anomalies suggest that there may be aspects of time that transcend our understanding of space, causality, and even reality itself. The arrow of time. The concept of time flowing in one direction, from past to present to future, is often referred to as the arrow of time. This arrow is deeply rooted in thermodynamics and entropy, with the second law of thermodynamics stating that entropy, or disorder, always increases over time. As systems evolve, they move toward a state of higher entropy, and this progression is thought to give time its forward direction. Entropy and the universe. The increase of entropy provides a macroscopic view of why time seems to flow in one direction. A glass shattering, for example, moves from a state of order to chaos. While this principle applies to everyday life, at the cosmic level it becomes more abstract. The universe itself is thought to have started in a low entropy state during the Big Bang, and since then it has been evolving toward greater disorder. The question, however, is whether time itself can be reversed. Temporal paradoxes and quantum mechanics. One of the most perplexing aspects of time is its relationship to quantum mechanics. The quantum world operates on principles that defy classical logic, and time appears to be no exception. In the realm of quantum physics, certain anomalies and paradoxes challenge our conventional understanding of time. Quantum entanglement and non-locality. Quantum entanglement is the phenomenon where particles become linked and instantaneously affect one another, no matter how far apart they are. Suggests that time might not be as absolute as we perceive it. When two entangled particles are separated by vast distances, changes to one particle are reflected in the other instantly, seemingly violating the standard notion of time. Time symmetry in quantum mechanics. Another mind-bending concept in quantum mechanics is time symmetry. Many equations in quantum physics are time symmetric, meaning they don't distinguish between the past and the future. This concept suggests that, on a fundamental level, time could move backward as easily as it moves forward, raising the possibility of time reversal under certain conditions. Black holes and time dilation. Black holes, the densest objects in the universe, provide some of the most extreme examples of time anomalies. According to Einstein's theory of general relativity, the intense gravitational fields around black holes warp space-time to such an extent that time behaves differently near them than in other regions of space. Gravitational time dilation. As objects approach the event horizon of a black hole, time appears to slow down relative to an outside observer. This effect, known as gravitational time dilation, occurs because the curvature of space-time near the black hole is so severe that the passage of time slows in proportion to the strength of the gravitational field. For an observer falling into a black hole, time would seem to slow as they approach the event horizon, and to an external observer, it would appear as though they never actually crossed the threshold. The fate of time inside a black hole. Once past the event horizon, it is still unclear what happens to time itself. According to current theories, time inside the black hole may cease to have any meaningful existence, collapsing to a singularity where the laws of physics as we know them break down. This raises an intriguing question. If time behaves differently inside a black hole, could there be places in the universe where time is entirely non-lunar, or behaves in ways we cannot comprehend? Wormholes and temporal travel. One of the most fascinating implications of general relativity is the possibility of wormholes, shortcuts through space-time that could, theoretically, allow for time travel. Wormholes, also known as Einstein-Rosen bridges, are hypothesized to be tunnels in space-time that connect two distant points in both space and time. If such structures exist, they could provide a means of traveling backward or forward in time, offering the tantalizing possibility of time travel. Time travel theories. Wormholes could theoretically allow an object to traverse from one point in space and time to another in an instant, bypassing the normal flow of time. This could offer solutions to some of the paradoxes in time travel, such as the famous grandfather paradox, in which a person travels back in time and inadvertently prevents their birth. Theoretical challenges. However, the concept of wormholes and time travel presents numerous theoretical challenges. For instance, it is not yet clear if wormholes even exist, or whether they could be stabilized enough for human passage. Additionally, the notion of time travel raises deep questions about causality and the potential for paradoxes, making it an area of continued theoretical debate among physicists. Cosmic time anomalies and the Big Bang. The Big Bang theory, which posits that the universe began as an infinitely dense and hot singularity, also brings with it deep questions about the nature of time. In the moments immediately following the Big Bang, time and space were so compressed that the standard laws of physics broke down. The beginning of time. The concept of a beginning to time itself is one of the most perplexing aspects of cosmology. If time began at the moment of the Big Bang, what existed before? Was there a before time? Could time be cyclical, with the universe undergoing infinite cycles of expansion and contraction, or does time itself have a finite origin? Cosmic inflation and temporal expansion. The theory of cosmic inflation, which describes a rapid expansion of space in the early universe, suggests that time and space may have evolved in ways that we cannot yet fully comprehend. Some physicists propose that the nature of time itself may have been different before the inflationary period, leading to a potential shift in our understanding of the temporal fabric of the cosmos, a mysterious fabric of the cosmos. While these anomalies represent the cutting edge of our understanding of time and its relationship to the universe, they also highlight the vast unknowns that still exist. Whether it is the bending of time near black holes, the quantum mysteries of entanglement, or the theoretical concept of time travel, these phenomena continue to defy our current understanding of how time functions at both the cosmic and quantum levels. In the end, time remains one of the greatest mysteries of the universe. It is an integral part of the cosmic structure, yet it eludes our full comprehension. The temporal anomalies that we observe may one day reveal deeper truths about the very nature of existence itself, challenging our notions of causality, reality, and the flow of time itself. Mystery 8. Ancient star systems, the first stars, and their secrets. The birth and evolution of stars are fundamental to understanding the history of the universe. However, one of the most intriguing mysteries lies in the existence of ancient star systems. One of the most striking examples of stellar remnants, still found in history, is the stellar remnants that have survived from the early stages of the universe. These stars, often referred to as population 2 and population 3 stars, provide a unique window into the early cosmos and the formation of galaxies, as they existed during a time when the universe was much younger and its chemical composition was vastly different from what we see today. Population 3 stars are the first generation of stars to form in the universe. These stars are thought to have formed roughly 200 million to 400 million years after the Big Bang, when the universe was still primarily composed of hydrogen and helium. Unlike modern stars, which are rich in elements like oxygen, carbon, and iron, population 3 stars were made almost entirely of hydrogen and helium, elements that were produced during the Big Bang, nucleosynthesis. These stars were likely massive, burning bright and hot, and they had short lifespans, ultimately collapsing into supernovae. Yet, despite their theoretical existence, no direct observation of population 3 stars has been made so far. Their remnants may still be detectable in the form of certain elemental compositions in ancient stellar populations, and it is believed that these early stars played a crucial role in the reionization of the universe, an event that occurred when the universe transitioned from being opaque to transparent. However, the lack of direct evidence for these stars makes their study one of the most perplexing challenges in cosmology. The mystery of population 2 stars. While population 3 stars remain elusive, population 2 stars provide another layer of mystery. These stars are older than the stars we typically observe today and are believed to be remnants of the early stages of the universe, formed from the gas enriched by the death of population 3 stars. Population 2 stars are found primarily in the halos of galaxies, as well as in globular clusters. They contain very low levels of heavy elements, also known as metals in astronomical terms, which suggests that they formed before significant stellar evolution and supernovae had occurred in their regions. One of the most notable aspects of population 2 stars is their age. These stars are believed to be some of the oldest stars in the universe, with ages ranging from 11 billion to 13 billion years. Some of them may even have been formed just a few 100 million years after the Big Bang, making them key witnesses to the early history of the universe. Their study could provide valuable insights into the processes that occurred during the first few billion years after the formation of the cosmos. The role of ancient star systems in understanding cosmology. Ancient star systems, particularly those that contain population 2 stars, are important to cosmologists because they provide clues about the early universe's chemical makeup and the conditions that existed shortly after the Big Bang. By studying these stars, astronomers can trace the evolution of elements in the universe, including the formation of heavier elements like carbon, oxygen, and iron, which are essential for life as we know it. Furthermore, ancient stars are believed to have played a pivotal role in the formation of galaxies. These stars formed in the early proto-galaxies, and their stellar remnants and supernova explosions contributed to the enrichment of the interstellar medium with heavier elements. Over time, these elements would have coalesced to form the first generation of galaxies, influencing their structure and growth. The study of ancient star systems, therefore, is essential for understanding the formation and evolution of galaxies and the universe as a whole. Search for population 3 stars. While population 3 stars are thought to have existed in the early universe, finding direct evidence of them is extraordinarily challenging. These stars would have been formed during a period when the universe was not yet capable of producing the complex elements found in later generations of stars, meaning they would have been composed almost entirely of hydrogen and helium. The first direct observations of these stars may lie beyond the capabilities of current telescopes, but astronomers are hopeful that future space observatories, such as the James Webb Space Telescope, JWST, could potentially identify signs of these ancient stars. The JWST, with its powerful infrared capabilities, is designed to detect faint light from the earliest galaxies and stars, including population 3 stars. If discovered, these stars could provide the final piece of the puzzle in understanding the first few 100 million years after the Big Bang. However, even if these stars remain elusive, astronomers have found indirect evidence for their existence. For instance, some distant quasars show an abundance of light elements like hydrogen and helium, but very few heavier elements. This could suggest that the quasar's light has passed through the remnants of population 3 stars or the gas clouds they created. Similarly, the cosmic microwave background (CMB) radiation, which provides a snapshot of the universe when it was just 3,800,000 years old, also carries clues about the conditions that led to the formation of population 3 stars. The fate of ancient star systems. The eventual fate of these ancient stars and their remnants is another aspect of their mystery. Population 3 stars, with their massive sizes, would have burned through their fuel at a rapid rate, ending their lives in spectacular supernova explosions. These explosions would have dispersed heavier elements into the surrounding space, contributing to the formation of later generations of stars. including the population 2 stars. Many of the remnants of population 3 stars, such as black holes and neutron stars, may still exist today in the cores of galaxies, particularly in the halos of the oldest galaxy clusters. However, these remnants are difficult to detect due to their distance from Earth and the fact that black holes and neutron stars do not emit visible light. Nevertheless, their presence can be inferred by the effects they have on nearby objects, such as the gravitational lensing of light or the bending of light from more distant sources. In addition to black holes, the death of population 3 stars likely resulted in the formation of exotic objects such as neutron stars and white dwarfs. These remnants of dead stars may continue to live on for billions of years, gradually cooling and fading into obscurity. Implications for understanding the early universe. The study of ancient star systems provides crucial insights into the processes that shaped the early universe. The chemical composition of these stars reveals much about the conditions in the early cosmos, as well as the evolution of galaxies in the interstellar medium. Furthermore, ancient star systems may hold the key to understanding the role of first-generation stars in the reionization of the universe. By unraveling the mysteries of ancient stars and their remnants, astronomers hope to gain a deeper understanding of the universe's formation and its evolution over the course of billions of years. As new tools and technologies allow us to peer further into the distant past, the study of ancient star systems will continue to offer a fascinating glimpse into the earliest chapters of the universe's history. Mystery 9. The Fermi Paradox. The paradox of silence, one of the most compelling and baffling mysteries in astrobiology and cosmology, is the Fermi paradox. The apparent contradiction between the high probability of extraterrestrial civilizations existing in the universe and the complete lack of evidence for or contact with such civilizations. This paradox is named after the Italian-American physicist Enrico Fermi, who famously asked, "Where is everybody?" during a casual conversation with colleagues in 1950. Given the vastness of the universe, with billions of stars and the Milky Way alone, many of which host planets in their habitable zones, it seems almost certain that life should exist elsewhere. The Drake equation, developed in 1961, estimates that there could be thousands or even millions of civilizations scattered throughout the galaxy. However, despite extensive searches for extraterrestrial signals and direct contact, there has been no conclusive evidence to suggest that we are not alone. The Fermi paradox presents an unresolved tension. If the universe is so large and so old, with countless opportunities for life to arise, why haven't we detected any signs of extraterrestrial intelligence? This question has stumped scientists, philosophers, and enthusiasts alike for decades, leading to a range of possible explanations, some grounded in science and others more speculative. The Great Silence. A universe full of stars, yet no voices. The scale of the universe adds weight to the paradox. There are estimated to be over 100 billion galaxies in the observable universe, each containing hundreds of billions of stars. Many of these stars are surrounded by exoplanets, some of which may lie within the habitable zone, the region where liquid water can exist, a key ingredient for life as we know it. The discovery of exoplanets, particularly those in habitable zones, has only intensified the questions raised by the Fermi paradox. With so many potential planets and stars, it seems plausible that at least some of them would host life capable of developing advanced technologies. However, we have yet to detect any signals or evidence of extraterrestrial intelligence. One of the most famous attempts to address this question is the Search for Extraterrestrial Intelligence, SETI, which uses radio telescopes to scan the skies for artificial signals. Despite decades of searching, no definitive signals have been detected. The Great Filter Hypothesis. One of the leading explanations for the Fermi paradox is the idea of the Great Filter. This hypothesis posits that at some point between the emergence of life and the development of an advanced spacefaring civilization, there is a significant barrier, an event or series of events that drastically reduces the chances of intelligent life evolving. The Great Filter could exist at any stage in the process, from the formation of life itself to the development of complex organisms, the rise of intelligence, or the technological advances needed for interstellar travel. The Great Filter theory presents two possibilities. Either intelligent life is extremely rare, and we are among the few civilizations that have managed to pass through the filter, or advanced civilizations tend to destroy themselves before they can achieve interstellar communication. The former suggests that the emergence of life capable of developing advanced technology is exceedingly rare, and we are incredibly fortunate to be one of the few such civilizations. The latter, more ominous interpretation implies that most civilizations may destroy themselves before they can reach the stage of interstellar communication, possibly due to self-inflicted catastrophes such as war, resource depletion, or environmental collapse. Other explanations for the Fermi paradox. While the Great Filter provides one possible explanation, numerous other theories attempt to resolve the paradox. Some suggest that extraterrestrial civilizations may be out there, but they are deliberately avoiding contact with us, either for reasons of cosmic zookeeping, a kind of hands-off policy to allow us to develop naturally, or because they view us as too primitive for meaningful interaction. This idea has been described in various ways, including the prime directive hypothesis, which posits that more advanced civilizations might have ethical concerns about interfering with less developed ones. Other hypotheses propose that extraterrestrial civilizations could be so far away, perhaps located in distant parts of the galaxy, that their signals are simply too weak or too spread out for us to detect with our current technology. In this scenario, it's possible that we are just too early in our technological development to recognize the signals of others, or that we're looking for the wrong types of signals altogether. For example, we might be searching for radio waves, while advanced civilizations may be using completely different communication methods beyond our comprehension. Another intriguing possibility is that extraterrestrial civilizations may have already visited Earth, but their presence went unnoticed, or we failed to recognize it. This idea plays into theories about UFOs and unidentified aerial phenomena, UAP, suggesting that alien civilizations may have visited our planet in the past, perhaps during ancient times, without leaving obvious traces or engaging with us in ways that would have been immediately apparent. The simulation hypothesis. One speculative answer to the Fermi paradox is the simulation hypothesis, which proposes that we are living in a computer-generated simulation. If our reality is indeed a simulation, the simulation's creators may have programmed it in such a way that we do not have access to the true nature of the universe. In this case, the apparent lack of contact with extraterrestrial civilizations could be a result of the simulated nature of our reality, designed to limit or control our awareness of a larger, more complex cosmos. While this idea may seem far-fetched, it has garnered attention from some scientists and philosophers, including prominent figures like Elon Musk. If we are living in a simulation, the lack of contact with other civilizations might be intentional, or the simulation itself may not model the presence of extraterrestrial beings at all. This concept shifts the Fermi paradox from a question about the physical universe to one about the nature of consciousness and reality itself. The search for answers. The Fermi paradox remains one of the most profound and enduring questions in science, and its resolution has far-reaching implications for our understanding of life, intelligence, and the universe. As technology continues to advance, particularly in the fields of astronomy and space exploration, we may be closer than ever to answering this mystery. Projects like the James Webb Space Telescope and the Breakthrough Listen initiative are pushing the boundaries of our search for extraterrestrial life, scanning distant stars and galaxies for potential signs of alien civilizations. However, the Fermi paradox is likely to remain a topic of fascination and debate for years to come, as the absence of evidence is not necessarily evidence of absence. Whether the solution lies in the rarity of life, the self-destruction of civilizations, or the fundamental limits of our perception, The question of where extraterrestrial life might be remains one of the greatest mysteries of the cosmos. Mystery 10. The fate of the universe. An infinite, expanding cosmos. As humanity continues to explore the mysteries of the universe, one question looms large over our understanding of cosmic existence. What is the ultimate fate of the universe? This question ties together many of the profound mysteries of cosmology and physics. Although we've uncovered much about the universe's early stages, from the Big Bang to the present, its future remains shrouded in uncertainty. One of the most captivating discoveries in modern cosmology is that the universe is not static, but instead expanding. In fact, the discovery of this expansion, made by astronomer Edwin Hubble in the 1920s, revolutionized our understanding of the cosmos. The expansion of the universe suggests that the universe was once concentrated in an incredibly dense and hot state, and it has been stretching and evolving ever since. Yet the question of what will happen to this expanding universe and whether it will continue to grow indefinitely, collapse upon itself, or reach some other fate has intrigued scientists for decades. Understanding the future of the universe requires examining various theories and observations about its structure, behavior, and the forces driving its expansion. The expanding universe and its implications. One of the key observations that shape our view of the future of the universe is the acceleration of its expansion. In the late 1990s, astronomers discovered that the universe's expansion was not slowing down, as they had once expected, but rather accelerating. This unexpected revelation came from the observation of distant supernovae, which appeared dimmer than anticipated. The acceleration was later attributed to a mysterious force, termed dark energy, which acts as a repulsive force, pushing galaxies apart. This discovery has profound implications for the ultimate fate of the universe. If the expansion continues to accelerate indefinitely, the universe will continue to stretch, causing galaxies to drift further apart. Over time, this process could result in a heat death, or big freeze, where stars burn out, galaxies drift beyond each other's light, and the universe becomes a cold, dark, and desolate place. This outcome is one of the most widely discussed scenarios for the future of the universe. However, not all theories point toward an eternal expansion. Some suggest that the universe's expansion could eventually slow down and reverse, leading to a big crunch. In this scenario, the gravitational pull between galaxies would overcome the expansion, causing the universe to collapse back in on itself. The result would be a singularity where all matter and energy are compressed into an infinitely small and dense point, much like the state of the universe at the time of the Big Bang. Theories of the universe's fate. Beyond the Big Freeze and Big Crunch, several other theories attempt to predict the future of the universe. One of the more speculative ideas is the concept of the Big Rip. This hypothesis suggests that as dark energy continues to drive the acceleration of the universe's expansion, it could eventually reach a point where the force becomes so powerful that it rips apart galaxies, stars, planets, and even atoms. In this scenario, the universe would end in a violent, catastrophic explosion of everything, long before the stars have burnt out or galaxies drift into isolation. There is also a possibility that the universe could experience a more cyclical fate. According to the oscillating universe theory, the universe could go through infinite cycles of expansion and contraction, with each Big Bang followed by a Big Crunch, only to start over again in an endless loop. This idea suggests that the universe is not a one-time event, but rather part of a never-ending cycle of birth, death, and rebirth. While this theory has not been proven, it offers a compelling alternative to a single, irreversible fate for the cosmos. Some scientists also speculate that the universe may eventually decay in a process known as a vacuum metastability event. In this scenario, the fundamental forces and constants of nature could change, causing the very fabric of the universe to unravel and collapse. Such a transformation would fundamentally alter the laws of physics and create a universe entirely different from the one we know. The end of time and space. As we ponder the fate of the universe, we are also confronted with more profound questions about the nature of time and space. If the universe eventually reaches a state of heat death, where all matter has spread out and stars have burned out, what becomes of time itself? Time, as we understand it, is tied to the movement and interaction of matter and energy. Without these forces at play, does time cease to exist? Would the end of the universe mark the end of time? Some theories suggest that even in the farthest reaches of the universe, time may continue in some form, as it is an intrinsic part of the fabric of space-time itself. However, if the universe continues to expand forever, with no energy sources or matter to interact, time may become irrelevant. The very idea of a beginning or end could lose its meaning in such a scenario. These contemplations about the end of the universe also touch on deeper philosophical questions about existence and the nature of the cosmos. Are we simply participants in a finite universe, destined to one day fade away? Or is the universe itself infinite, constantly evolving and regenerating in ways we cannot yet comprehend? Cosmic endgames and the search for meaning. While we may never know the true fate of the universe in our lifetimes, the search for answers continues to inspire scientific research and discovery. As we look to the stars and contemplate the cosmos, the fate of the universe becomes a symbol of our quest for knowledge and understanding. Whether the universe ends in a fiery collapse, a silent freeze, or a cyclical rebirth, the mysteries of the cosmos offer a canvas for the imagination and a reminder of the vastness and complexity of the universe we inhabit. In the end, the fate of the universe may be one of the greatest mysteries of all, an unsolved riddle that challenges our understanding of time, space, and existence itself. But for now, the journey to unravel its secrets continues, pushing the boundaries of human knowledge and forever expanding our sense of wonder. As we continue to explore the cosmos, these unanswered questions remind us of the vast mysteries still waiting to be uncovered, leaving us to wonder what the future holds for the universe. Conclusion. Unraveling the mysteries of the cosmos. The universe, with all its vastness and complexity, continues to confound our understanding. From the haunting emptiness of cosmic voids to the bizarre behavior of phenomena like dark matter and quasars, we find ourselves on the edge of discovery, yearning to understand the hidden forces that govern our reality. Each mystery we explore brings us closer to unraveling the nature of the cosmos. Yet, paradoxically, every answer seems to lead to even more profound questions. We've ventured through some of the most perplexing anomalies, the enigmatic dark energy that drives the acceleration of the universe's expansion, the impossible nature of time as we perceive it, and the ongoing mystery of our very existence within the vast multiverse. These cosmic phenomena hint at deeper truths about space, time, and the forces shaping our universe. As we look at these anomalies, we realize that for every discovery made, the universe seems to reveal yet another layer of its complexities. The journey to understand the universe is as mysterious as the phenomena themselves. The voids in space, the unexplained motion of galaxies, and the potential existence of wormholes and parallel universes push the boundaries of science and technology, calling upon humanity's greatest minds to peer further into the unknown. Yet, despite the advances in technology and our growing understanding of cosmic phenomena, we are still confronted with questions that cannot be answered by current knowledge alone. The Fermi paradox poses a question that not only reflects our search for life beyond Earth, but also challenges our understanding of the universe's vastness and its potential for intelligent life. The idea that we may be alone or the only ones to have ever reached such a level of awareness adds a deeper layer of mystery to our existence. It suggests that the universe is far more intricate, beautiful, and elusive than we can comprehend, reminding us of how much we still have to learn. In contemplating the fate of the universe itself, we are left with questions that may never be fully answered within our lifetimes. But our pursuit of those answers is what defines us as explorers. What we learn today shapes our future, and each discovery opens new doors to questions that may one day change our perspective on everything we know. The mysteries of the universe are far from solved, and in many ways they may never be. But that is part of the beauty of the cosmos. Each unexplained phenomenon fuels our curiosity and drives us to ask the bigger questions about the origins, nature, and ultimate fate of everything around us. And it is through this ongoing quest that humanity will continue to evolve, learning not only about the universe, but also about ourselves. As we close our exploration of these cosmic anomalies, it's important to remember that the universe is an ever-changing, ever-evolving puzzle. While many questions remain unanswered, it is this very uncertainty that propels us forward, encouraging us to keep searching, keep questioning, and keep marveling at the wonders that lie beyond the stars. The journey of discovery is endless, and with each mystery we uncover, the universe only becomes more fascinating.